Hi guys, welcome to the lecture number 10th of NLP series. I know the NLP series is going great, and yes, we are taking our time in order to just investigate basic concepts so that scaling up when it comes to industry ready NLP applications wouldn't be a task. So first of all guys, today we'll be talking about word embeddings. Now guys, we are slowly moving in the direction where we would start incorporating modern NLP techniques, okay, which is specifically based on LLMs. Not we haven't reached there, but we are in the, perhaps I'll say, the first stage. So guys, first of all, you need to understand why word embeddings are important. The idea is that first of all you need to make an assumption. Okay, to some people this is an assumption, to me this is a fact. It's your choice on which side you want to be. The main thing is that the words, essentially words have captured words have captured the meaning of the world. So guys, this is a fact to me. To some people, this is an assumption. Now, coming from the fact that words are so important, that because of words we are able to capture the meaning of the life. So we have so much corpus available guys. By corpus I mean text. Okay, we have so much enormous amount of text which is available to us, which is because of internet, right? So we have a lot of text available on internet. We have a lot of books, we have a lot of social media sites, we have a lot of research sites, and then we have some individual data as well. Essentially individual data is sort of private data, okay, because a lot of companies also have their own data sets and all, and those are nothing, those are private data sets, okay. So in case, let's say you want to win the AI race, right? You want to win the AI race and create the best LLM. So maybe for some use cases, having this access to private data would also be a key there. Now, the core understanding is, as I said, that words have meaning. Okay, guys, tell me. We have discussed about logistic regression, we have discussed about gradient descent, we have discussed about some mathematical terms other as well. So from your childhood guys, you would be seeing that whenever you apply any sort of maths, okay, I don't want to tell you that uh, what we exactly do yet, but everything will come in this course. But from your childhood, tell me, you've been applying maths, studying maths throughout. Now whenever you're studying or applying maths guys, you can't directly add to text. Like you can't add king plus men. What would be the answer to it? Come on guys, this type of addition is not possible. So any mathematical operation, maths is specifically applied on numbers. So if you want to capture the meaning of the world, and you want to do it with the help of numbers, right? You want to do it, you want to model the world, right? Essentially we are trying to model the world, okay, we are trying to model the world. Now if we wish to model the world, we would need to convert our knowledge base. So what is our knowledge base? Our knowledge base is text, so we need to convert text into numbers. Simple guys, there is no second or third degree explanation to it. When your texts get converted to numbers, okay, yes, obviously you would understand, right? Everything is being done at a vector level, so we can call it as vector. When your text gets converted to vectors, that essentially is your embedding. Because once you have converted your text into vectors, you can apply any maths operation, any sort of gradient descent you can apply, right? So we have seen gradient descent as well. So essentially guys, that's the essence of it, right? Even descent, the main equation was W old minus eta, rate of change of loss with respect to W old. Now this is a mathematical equation, right? You need to take partial derivatives of the loss function with respect to the weights, right? Then you have seen this equation also, y is equal to x of w plus beta. Let me rewrite it. X of w plus b. Now tell me guys, x, how will words extensively be text or x? So you need to convert the words into numbers or vectors. Now this process is known as word embeddings. But now guys, because we are trying to move towards an era of modern NLP, obviously it will take some time for me also to uh, make you guys fully aware about why modern NLP is very important. But yeah, fundamentally guys, fundamentally, at a very fundamental layer, now what happens is that essentially your words are converted into vectors with the help of neural networks. Okay, your words are converted to vectors with the help of neural networks, and these neural networks have captured the semantic meaning, right? So essentially what happens is that entire I mean most of the words can be written in the form of a vector like this. Let's say point 0.3, point 0.2, this and point 0.9. Let's say the dimension of this is 300. Okay, this is 300 cross 1. Okay, now trying to understand, this is essentially a column vector. Okay, now the main thing that I wanted to show you is that you have words. These words would get converted into a vector like this. How it is getting converted? With the help of a neural network. Slowly we'll understand everything. So now you have understood the essence and why we need to capture the idea of words into vectors. And yes, now let's just move to some basic methods. So today we'll be discussing two methods. One is term frequency method and another one is TFIDF. This is term frequency inverse document frequency. Don't worry about these methods guys, no one uses it right now, but yes, important to just get a glimpse of how earlier text modeling used to happen. And don't worry, I have code snippets and everything with me. I'll share that with you as well. So let me just close this thing and let's just go to the collab notebook that I've created. So guys, let's just try to see that what is happening. Okay, I've created a collab notebook which is very extensive in order to understand these two concepts. So guys, see, this is even the first step of the transformers architecture. Okay, so what is transformers? Transformers is the main underlining type of neural network which is used in all LLMs today. Okay, now the major thing is that's there. Now the thing is that, see, even the first step in the transformers is that your inputs, that is your text input, would get converted into input embedding or word embedding. Okay, now let's move ahead. So today, as I mentioned, that we'll be talking about two methods, two popular methods. One is term document matrix and another one is TF-IDF, term frequency and inverse document frequency. Okay, don't worry about terminology, we'll see everything. Now see guys, what is term document matrix? It's very simple guys. A matrix where each row represents a word, each column represents a document, each cell contains the frequency of item in the document. So let's just try to see. This is very simple guys. Just try to see this example. So guys, these are four plays of Shakespeare and these are four words. So at every row level you will have words and at every column level you have the document. Okay, so what does this term document frequency mean is, if you will see this matrix, what does this mean? This means is the word battle here, as you like it, occurs once. Battle in 12th night doesn't occur. Battle in Julius Caesar and Henry V occurs more often. So probably one thing is there that Julius Caesar and Henry V, this is Henry V I guess, not sure. So the idea is that battle is more frequently occurring in these two type of plays. So if you would have studied about Shakespearean's play, you might relate to it, right? So let's say wit, right? Wit is more occurring in these two things, and battle is occurring in these two things. So maybe there is some sort of genre classification which you can do, that these two belong to a similar genre and these two belong to a similar genre. Okay, I haven't like read any of them. I'll read all of them now, but yeah, that's fine. Now the main thing is, guys, once you can create a term document frequency, you can create compute vector similarities as well. So we have talked about vector similarities, right? Okay, we have talked about vector similarities. I'm not sure, but still let me do that with you guys. Let me just again share my iPad, and then we can get restarted on the part where I understand, make you understand vector similarities. It's very simple, guys, nothing very difficult. It's just a little bit of maths. Don't worry, we'll see that as well. So guys, as I said, that when it comes to modern NLP, we'll have words which would get represented as vectors with the help of neural networks, right? Now the thing that you need to take care of is that why, like, there is the essence with vectors, right? The essence with vectors is that there is something known as vector similarity. So if you have two vectors, okay, if you have two vectors and they carry same meaning, not same, similar meaning, then what will happen is that their cosine similarity will be large. So how is cosine similarity computed? Cosine similarity is essentially a vector dot b vector modulus a into modulus b. So let's say you have two vectors, 1 0.1 0.2 0.3, and you have another vector 0.2 0.4 0.9. So how would you compute the cosine similarity, guys? 0.1 into 0.2 plus 0.2 into 0.4 plus 0.3 into 0.9, and here you would have 0.1 square plus 0.2 square plus 0.3 square into 0.2 square plus 0.4 square plus 0.9 square. So guys, please do the math and tell me the answer also. I wish I would have had the energy to do this type of maths now, but yeah, I don't have that energy. But yeah, this is essentially how cos theta gets compared. And guys, cos theta ranges from -1 to +1. So if the values are close to 1, that means the vectors are related to each other. Okay, now that is there. Now let's just close it and let's just move to the code snippet. So guys, we were studying about term document frequency, right? You have seen how I'm able to compute term documents frequency, and now I'm trying to compare fool and wit. Okay, so these two, see, the similarities between fool and wit is 0.93, and the similarity between battle and good is 0.65. So see guys, this is having high cosine similarity. Okay, this is how you compute it using numpy, which is okay. Now no one like, you don't have to do it for the timing, but still it's good to know. So this is how you compute, and this is how you get the cosine similarity between two vectors. So guys, fool and wit have a highest cosine similarity based on their presence in our data. And that is done. So guys, that is term document frequency. But again guys, this is not a good method. It is very brute force method. Okay, it's more like that, like, it just is counting, right? Counting is the bare minimum thing anyone can do. And moreover guys, there are few common words, right? Like this example says that good is a common word, right? Good can occur in any sense. Let's say you're writing a painful satire, right? And you would use the word good so many times, and if you would just quickly go on the basis of its count, it would seem that hey, good is attributed to happiness, maybe the text is attributed to happiness, but it's a on satire on the pain, right? So you need to understand that what usually happens is that we need to capture the correct meaning. That is where neural networks win, and they win by a big margin. So that's okay, that's fine. We'll go there as well, slowly. So guys, see, this is just a 2D plot which I have plotted. What I have plotted, guys, I'll explain you. So what I was trying to showcase in this chart is words vector in 2D space. So as you like, it is a Shakespearean play, and the 12th night is a Shakespearean play. So what is this point? This point is plotted as 0, 1. So in x-axis it is on 0, and on y-axis this is at 1. What does this mean? This means that in the play As You Like, battle occurs 0 times. In the play The 12th Night, battle occurs 1 time. So this is just how I have plotted this. So essentially the idea is that similar words, okay, if there are multiple words over here in this 2D space, so these words might have similar meaning, these words might have similar meanings, and these words might have similar meanings. Okay, this is just 2D representation of the same. Now guys, let's come to TF-IDF. So guys, see, TF-IDF is another technique. Again, it is not used nowadays, but it's good to know, right? It's good to know, there's nothing harm in there, and I won't be spending a lot of time as well. So see guys, let me just increase the dimensionality. Yeah. So see guys, what is TF-IDF? TF-IDF stands for term frequency inverse document frequency. So guys, see, I'll directly explain you with an example, so that we can save a lot of time. So see guys, this is the example. The cat sat on the mat. So let's just compute TF-IDF for the word cat and the. Now what is first of all you need to do is you need to compute term frequency. So term frequency is number of occurrence the word has occurred in the sentence divided by the total number of words. So 1 divided by 1, 2, 3, 4, 5 and 6. So you get this 1 by 6, and for the it is 2, like, because it is occurring 2 and denominator same stays same, because that's the number of words in the sentence. So it's this. Now you need to you need to calculate inverse document frequency. So inverse document frequency is log of total number of documents. What are the total number of documents? 3 divided by number of documents containing the term t. So we are, how many has cat? So 2 has cat. So log 3 by 2 is this, and then you just have to multiply it. Okay, so see guys, for cat you are able to see that TF-IDF came out to be this, and for the it came out to be 0. Now why is this coming, and this essence is important? So guys, see, there are few words like the, uh, on, the, and similar words which might occur a lot of time, but they actually don't have any meaning. So how did TF-IDF improve from the normal term document way? Is that it told that hey, it's good that there are few words which occur a lot of time. So if I can scale down it with the help of logarithmic properties, it would give me the true essence of word, because you're able to see that the cat has a higher term uh, TF-IDF, but the word the has 0. So see, cat has low but non-zero TF-IDF, indicating somewhat important, and the has a TF-IDF of 0 despite appearing frequently, because it is in every document. So if a word is in every document, probably it is not that important. So that's how TF-IDF also works. So guys, see, these are mathematical techniques, which is good. But now we have neural networks, and probably they are going to come to rescue us. Slowly we'll reach there as well. Guys, please subscribe to the channel. And yes, both of these methods are not used anymore, but it's just a interpretation of how words are expressed as vectors, and how these vectors essentially capture the semantic meaning of the text, and essentially the text is a representation of word. So on that note, I would like to end, and I hope you have a great day, and please subscribe to my YouTube channel. Thank you and enjoy.